Okay, so welcome to this class for ME 243. So this is the first class now. So the first topic that I am going to cover is vector spaces. Okay, so as I already indicated that this is going to be an advanced class. The concept of vector spaces is a little bit abstract. Okay, so you have to be a bit careful about how you use this. So vector spaces. So as I said, this is a very abstract concept which may take a little bit of time getting used to this concept here. So first let me tell you what the notation that I am going to use. So R is going to denote the space of real numbers, set of real numbers. And so a vector space or linear space is a set V equipped with an addition function on V dot V. So this is denoted by plus and a scalar multiplication function on R plus V. Okay, so what do these symbols mean? So here V cross V to V means that I am taking the first element from V, which is this vector space. I am taking the second element from V, and then there is a mapping to V itself. Okay, so that is what we mean by this symbol. Similarly here, I am taking the first element from the space of real numbers and operating on a member of the vector space V, and then I am getting another member which is also lying in the vector space V. Okay, so that is the meaning of these symbols here. So with satisfy the following conditions. Okay, so first one is commutativity. So for all UV belonging to V, U plus V is equal to V plus V. So you will see that most of these properties, they will be very similar to properties of real numbers, very similar to that. But as I said, that this concept is a very abstract concept. Okay, so the real the set of real numbers is an example of a vector space, but a vector space is much more general than that. Okay. So this is the first axiom that it has to satisfy. Then let us now talk about the other axioms. This particular part here. Second one is associativity. So for all U, W, V, U plus V plus W is equal to U plus V plus W. And the third is existence of a zero element. So there exists a zero belonging to V such that U plus 0 is equal to U. And fourth is existence of negative elements for each U V there exists. So this symbol here means there exists. This symbol here is of course the vector space. This means belongs to. Okay, so these are some of the standard symbols that I will be using. This part also will erase. There exists a negative element minus U, again belonging to V, such that U minus U is equal to 0. Okay. Then distributivity. With respect to addition of vectors. So for all alpha belonging to R and U V belonging to V, alpha times U plus V is equal to alpha U plus alpha V. So this is distributivity with respect to addition. Then let us go to the next axiom. Sixth one. So distributivity with respect to scalar addition. So for all alpha theta belonging to R, and for all U belonging to V, alpha plus beta times U is equal to alpha plus alpha U plus beta V. Okay, and then the seventh property is associativity. So for all alpha beta belonging to R and for all U belonging to V, alpha beta U is equal to alpha beta of U. So this is how we define this particular operation here of associativity. And then the eighth property is identity in scalar multiplication. Okay, so here for all U belonging to V, 1 times U is equal to. So this 1 here is the identity element. So if the identity element multiplies any element U, you get back U. Okay. So as I said, there is an analogy with just numbers. So here, just if you multiply any number by 1, you would get the same number, right? So similar to that, this is an identity in the scalar multiplication. So, so one important thing is that you don't have to memorize all these 8 properties, but these are the, so how do you test now whether something is a vector space? So you first have to define the addition operation, you have to define the multiplication operation by the scalar, and then you have to test whether all these axioms are satisfied. Okay, if all these axioms are satisfied, then it is a vector space. As simple as that. Okay, so that is how we define this vector space. So we'll, of course, as I said, that this is a very abstract concept, but we will, what we will do is that we will give some examples, and then things will become much more clear. So okay, so let us look at some examples now. So, examples. Rn equal to so whenever I write this colon equal to, that means that this is a definition. Okay, so colon equal to always means definition. So I'm defining this Rn as the set of these numbers u1, u2 up to un, each ui belonging to R. Okay, so each ui belongs to R. So it's just a collection of n real numbers, basically. Okay, so that is Rn, and then so as I said that. Whenever you talk of a vector space, you always have to define what you mean by the addition function. Okay, so that is by the addition function and by the scalar multiplication function. So that definition should always accompany the definition of a vector space. You should never forget that. So for this particular space that we have defined, the addition and scalar multiplication are as follows. Addition is as follows. So this is u plus v is defined as u1 plus v1, it is defined by u1 plus v1, u2 plus v2, and so on, un plus vn. Okay, so this is how we define addition, and this alpha u. So this is how we define the scalar multiplication. So that is alpha u is equal to alpha u1, alpha u2, and so on up to alpha un. Okay. So this is one example of a vector space. Then another example is the space LP. Okay, so let us define that. So if P is a real number which is greater than 0, so this is just a real number, and the domain is the real line interval from 0 to 1. So that means I will write this as LP 0, 1. I will again define this as the set of all functions such that integral from 0 to 1 of f of p times dx is bounded. So that means, so okay, so how do you interpret whatever I have written here? So this p is this number here. This space LP is defined. So you always have to define the domain. Okay, so this is very, very important. Whatever functions may lie in LP on 0, 1, for example, will not lie in 1, 2 if you change the domain. Okay, so defining the domain is very, very important. So LP associated with the domain 0, 1 is the space of all functions. So what this statement, the way it is to be read is, it is the space of all functions. So this colon means such that they have to satisfy this particular constraint here. So integral of mod f raised to p dx from 0 to 1, because 0 to 1 is the domain that we are talking about. So those are the integration limits that should be bounded. Less than infinity means it should be bounded. It should not become unbounded. So for example, if I try to integrate log x from 0 to 1, right, then that is unbounded, right? So something like that. So basically it is a set of all functions such that this integral is bounded. So that is a space of all LP. As I said that the definition of a vector space is incomplete unless you define what is the addition function and what is the multiplication function. So let us now define what we mean by the addition function and the multiplication function. So f plus g, so this is the addition function, is equal to f of x plus g of x for x belonging to 0, 1, and alpha f times x is equal to alpha times f of x. Okay, so this is how we define the addition and the scalar multiplication function. So I keep repeating this because this is a very important point here, that you have to define what you mean by an addition function and by the scalar multiplication. Without that, the definition of a vector space is incomplete. Okay, so this is very important. You have to define those things. Fine. So now we have given these examples. So actually, later on we'll see that Rn is a finite dimensional vector space, whereas LP is an infinite dimensional vector space. Okay. So what do we mean by a finite dimensional vector space? So that means there are a finite number of basis vectors. So we'll soon introduce this concept of basis vectors. So whereas for LP, there is no finite set of basis vectors by which you can express a given function. Okay, so that is what we mean by infinite. So you need infinite number of elements to express any element in the LP here. Okay, so now let us introduce the concept of linearly independent elements of V, and then we will also define what we mean by a basis. Okay, so let us start that. So now a subset. So we'll define what we mean now by linear dependence and linear independence of elements of this vector space. So a subset U1, U2, and so on to Un of V is said to be linearly dependent, linearly dependent if and only if. So many times, so these are some of the abbreviations that I will use. IFF will stand for if and only if. Okay, so these are some of the abbreviations that I will use here. If and only if there exists. So again, this symbol is there exists. Scalars alpha 1, alpha 2, and so on up to alpha n. Not all 0, such that alpha 1 U1 plus alpha 2 U2 plus and so on plus alpha n UN is equal to 0. So, okay, so you have to be very careful when you read these definitions. Okay, so I have underlined some of the key terms in these definitions here. So first is that this set is said to be linearly dependent if and only if there exist scalars alpha 1 up to alpha n, not all 0. That means some of them can be 0. Okay, so it's not that all of them have to be non-zero. So some of them can be 0, but at least there has to be at least one element which is non-zero. So that is what we mean, not all 0, such that this particular condition is satisfied. Okay, so if this condition is satisfied and if not all of them are 0, then that means this is a linearly dependent set. Okay, you want to use. Okay, fine. Similarly, so then from this, what is linear independence will follow, right? So thus, a subset U1, U2 up to UN of V is linearly independent now. Independent linearly independent if and only if the equation alpha 1 u1 plus alpha 2 u2 plus up to alpha n un is equal to 0 implies that alpha 1 is equal to alpha 2 is equal to alpha n is equal to 0. Right? So from this definition we get the definition for a linearly independent set. So that means this equation alpha 1 u1 plus alpha 2 u2 up to alpha n un is equal to 0 implies that each of these constants is 0. So just I will give a very simple example so that you will understand this concept very easily. Suppose if I take E1, right, just take the Cartesian basis. If you take E1 to be 1 0 0, right, E2 to be 0 1 0, 0 1 0, and E3 to be equal to 0 0 1. For example, if you just take the standard basis, right, and now if I write alpha 1 E1 plus alpha 2 E2 plus alpha 3 E3, then you will see that this is going to be alpha 1, alpha 2, alpha 3, right? And if this is equal to 0, then this implies that alpha 1 is equal to 0, alpha 2 is equal to 0, and alpha 3 is equal to 0, right? So this is a very nice example, very simple example to show what we mean by linear independence, right? So this E1, E2, E3 are linearly independent, right? We can conclude from this. So that first basically if we form this equation and if that implies that each of the constants is 0, then that means they are linearly independent. So here it is obvious that E1, E2, E3 are linearly independent. So we have shown that actually they are linearly independent by showing this that this property is satisfied here. Fine. Then now let us move on. So using this concept of linear independence, we will now define what we mean by a basis. Okay, so this is again a very important concept. So just in this particular example, E1, E2, E3 is the basis for R3, right? The three-dimensional vector space R3. So similarly, now let us talk about a general vector space and what constitutes a basis for that particular vector space. Okay. So let us define what we mean by a basis now. So a subset E1, E2 up to En is linearly of V is said to be a basis for V if one is that E1, E2 up to En is linearly independent. And the second property is that any element of V can be expressed as a linear combination, of E1, E2, and so on up to En. That is, if U belongs to V, then U is equal to U1 E1 plus U2 E2 plus UN En. Okay. So these U1, U2, UN up to UN are known as the components of U with respect to the basis E1, E2 up to En. Okay, so this U1, U2 and so on up to UN are known as the components of U with respect to the basis. So all these statements are very, very important. Please note that with respect to the basis, E1, E2, and so on up to En. So as I keep repeating this, that you have to be very careful in the way you interpret all of these statements here. So for example, we have said that it is said to be a basis if this property is satisfied, that means the E1, E2 up to En is linearly independent, and also any element can be expressed as a linear combination of E1, E2. So both these properties have to be satisfied. You cannot say that okay, it is just linearly independent, hence it's a basis. So so actually, these concepts are not very complicated to understand if you take a concrete example. Okay, so let us just go back to the example of R3. So suppose if I take now E1, right, equal to 1, 0, 0, right, and if I take E2 to be equal to 0, 1, 0, right. Now I will say that is this a basis now? E1 and E2, are they a basis for R3? Okay, so now you can see very clearly that E1 and E2 are linearly independent, right? So they satisfy the first property. E1 and E2 are satisfying the first property, but they do not satisfy the second property, right? For example, the vector, suppose if I have the vector 0, 0, 1, right? I cannot express the vector 0, 0, 1 as a linear combination of E1 and E2, right? So just simply E1 and E2 do not constitute a basis. So basically, they do not satisfy this particular property, that any element of V can be expressed as a combination of E1, E2 up to En, and so hence just E1 and E2 doesn't constitute a basis. Now if you append E3 also to that, then of course the whole thing is a basis. So as I said, whenever there is a confusion about whether about any of these issues, you should just take simple examples like this, like the way I am doing here, and then that will clarify, some of these concepts here. Fine. Okay, so let us move on then to the next concept, which is that so we have the following theorem now regarding the basis. Another important thing that I forgot to mention here, and that this statement is also very, very important with respect to this basis. Okay, so if I change the basis, then the components will change. So again, as I said, that you keep, if you are not able to understand a certain thing, just think of an appropriate example. So suppose I have this as my basis. Suppose now E1, E2, E3 is a basis, right? Then some vector will have components with respect to this basis. Now I can also take this as my basis: 1, 0, 0, 1, 1, 0, and 1, 1, 1. I can take this as my basis, right? Because they are linearly independent, and any vector can be expressed in terms of these three vectors. So the components with respect to this basis, so this I will call as the canonical basis or a natural basis, whereas this basis is some contrived thing, some artificial thing, right? So, but still it's a valid basis. Mathematically speaking, there is nothing wrong with this. So the components of a particular vector with respect to this basis will be different than the components of a particular of that same vector with respect to this. So that is why this statement is very important. Whenever you talk of components, it has to be components with respect to a basis. There is no such thing as just components. Okay, component means always with respect to some basis, and you have to say with respect to which basis you are bringing that. So some of these statements are very, very important. That's why I am underlining those statements here. Fine. Now, as I said, let us look at the characterization of basis vectors now. Essentially, in this particular course, we will deal exclusively with finite dimensional vector spaces. So the LP, which was an example of an infinite dimensional vector space, we will not have the occasion to use that at all. So we can sort of exclusively focus on finite dimensional vector spaces, and so most of the theorems that I will be talking about will be dealing only with finite dimensional vector spaces here. Fine. So theorem now. So all bases for a given vector space or a given vector space I will not say, I mean, it is obvious because, so I'm talking only of finite dimensional now, okay? So I will not keep repeating that I am talking only of finite, because in an infinite dimensional there is no, same number has no meaning anyway, right? So whenever, now onwards, whatever I am discussing is mostly for finite dimensional spaces only. So all bases for a given vector space contain the same number of elements. Contain the same number of elements. So what that means is that again, let us take the case of three-dimensional vector space R3. Right there, you cannot have one basis which is only two vectors and another basis which is four vectors. So you cannot have bases which have different number of elements. Okay, so they all have the same number of elements. But see, many of these statements, they are intuitively obvious but very difficult to prove, as you will see. Okay, so and the proofs, one has to be very careful that we are not leaving some case which is not thought of. So one has to be very careful in these proofs. So let us just look at the proof for this one. So suppose now that E1, E2 up to En and E1 star, E2 star up to En star are basis for me. So these are now two bases. So sorry, here I should have M. Sorry about that. So I mean, basically we cannot assume. So we want to prove that. So we want to prove basically that this N is equal to M. That's what we want to prove actually. So we start with the assumption that N and M can be different. And so these are the two different bases that we have. Okay. Now, so you can express now since so every since now this E1, E2 and so on, En is a basis, right? Is a basis. Since Ei star belongs to V, right? So this is a basis, right? So it obviously belongs to the vector space. So every element of Ei star, this belongs to V, and hence it can be expressed in terms of this basis, right? Because it's an element of this vector space here. So we can write, I can write that Ei star, I can write as equal to beta Ij Ej. So in this particular course, because as I said, this is an advanced course, I will be assuming that you know initial notation. So that is not something that I'm going to cover in this particular course here. So here, J is a dummy index and I is a free index. So it is assumed that you know this. So this is like E1 is beta 1 E1 plus beta 1 2 E2 and so on. Okay, so that is. So I'm going to assume that you already know that you're already familiar with initial notation here. Okay, so now if I consider the linear combination alpha I Ei star. So let us consider this. So this is equal to, suppose, beta Ij. So alpha I is beta Ij, and then this is alpha I times Ej. So suppose if this is equal to 0, okay. Then by the linear independence of the Ej's, right, this will imply, so since the E1, E2 and so on is linearly independent, and why is it linearly independent? Because it's a basis, right? E1, E2, E up to En is a basis, so by definition this is linearly independent. So because it is linearly independent, these coefficients have to go to 0. Correct? So this, so if you take that, if you start from this equation, then what you get is that beta Ij alpha I is equal to 0. And so for this, the index I runs from 1 to up to m, and the index j runs from 1 to up to n. So remember that m and n can be different at this particular stage here. Okay. So now we have this. So this is actually like a matrix. It's a rectangular matrix. Remember, it's not a square matrix because n is not necessarily equal to n. So this is a rectangular matrix multiplying a vector, giving another vector. So that is how this statement is to be interpreted. Okay, now let us look at the implications of that particular statement here. Alright, so, okay, fine. Okay, so you will get now that, so let now m be greater than n. Okay, so what is this? See here, if you see, that is the m is actually the number of the unknowns. Okay, so this is like a known matrix. This is the vector, and this is equal to 0. So now this is the number of unknowns. So the number of unknowns is greater than the number of equations. If we take this case that m is greater than n, because alpha i's are the unknowns that you are solving for, and they are m in number. The number of unknowns is greater than the number of equations. So in that particular case, when you have more number of unknowns than the number of equations, you can choose some of them to be non-zero, right? And so a non-trivial solution for alpha i's will exist in that particular case, right? So this, so the number of, let me just say that here. So number of unknowns is greater than the number of equations, right? And so non-trivial solution exists. Non-trivial solution exists. So what does that mean? That means that there are some alpha i's which are non-zero, right? You can always find some alpha i's which are non-zero. See, suppose this has been an n by n matrix such that beta ij, the determinant of beta ij is not equal to 0, then alpha equal to 0 is the only solution. So that is the trivial solution. But here, non-trivial solution means, trivial solution means all of them are 0. That is what we mean by a trivial solution. Non-trivial solution means some of the elements are non-zero also, can be non-zero. So that is what we mean by a non-trivial solution. So thus there exists. So thus there exists. So again, this symbol means there exists alpha 1, alpha 2 up to alpha n, not all zero, such that. So we started out with this, right? So now what we have concluded is that if this is equal to 0, then still there exists this alpha 1, alpha 2, alpha n not all 0, such that this alpha I, EI star is equal to 0. So that means this is a linearly dependent set, right? Because there are elements alpha 1 up to alpha n not all 0, such that this equation holds, right? So that means your EI star is a linearly dependent set, but that's a contradiction, right? That's a contradiction because EI star is also basis. So by definition, the EI star are linearly independent, right? Because it's a basis, it's a linearly independent set. So we have reached to a contradiction. So that means whatever we have assumed is wrong, correct? So because whatever we have assumed is wrong, we have reached to a contradiction. So we cannot have m greater than n, basically. Okay. So let us just write that here. Fine. So okay. Yes. So this implies that the EI star set is linearly dependent, right? Dependent. So this is a contradiction. Since, as I said, since EI star is a basis, right? So by definition, it has to be linearly independent. So it cannot be linearly independent, right? So that's the contradiction that I reached to. Hence, so let me just write it here. So m has to be thus. So I will just state the conclusion from this. So thus m has to be less than or equal to n. Okay. Now what you do is now you take now take m less than n. Okay, so just we took m greater than n. Now we'll take m less than n. Again, we'll reach to a contradiction. So that means n has to be equal to n. So that is the way the proof is proceeding. So here now, so now what we do is reverse the roles. Okay, reverse the roles of E1, E2 up to En, and E1 star, so on up to En star. So basically, wherever EI star was occurring, you put EI, and wherever the EI was occurring, you put EI star. So just reverse the roles of EI and EI star. Again, you will reach to a contradiction, right? Because there is nothing special about EI and EI star. They are just two different bases. So same arguments will go through and will again reach to a contradiction. So again contradiction, right? So again reach a contradiction, right? Same contradiction, again reach a contradiction. So thus the only possibility that is left is that n should be equal to n. Thus n has to be equal to n. So what we have, so basically what this theorem says is that if you have two different bases, okay, for a finite dimensional vector space, then both those bases should have the same number of elements, right? So that is the conclusion from this particular from this particular theorem. Okay, fine. So now we'll move on. Next thing. Okay, so yes, okay. So thus now vector space V is said to be n-dimensional it contains a basis with n elements. If no such finite n exists, then the vector space is infinite dimensional. It is infinite dimensional. Okay. So I have already given you an example of an infinite dimensional vector space, that is LP, right? That is an infinite. So basically, you cannot express an element of LP using a finite number of elements of basis vectors, basically. So you will need an infinite number of elements. So that is very difficult to prove, incidentally. So it is not a trivial proof to show that LP is infinite dimensional. But as I said, that for the purposes of this class, we will be focusing exclusively on finite dimensional vector spaces. So you need not worry too much about the infinite dimensional vector spaces here, right? But you should know, but at least you should know what we mean by an infinite dimensional space. So I'm just giving you the definition of an infinite dimensional vector space here. Fine. Then now, so again, let us just give some examples. So here, basically, if a space is n-dimensional, all the bases will have an element, right? Because we have just proved that you cannot have one basis which is less than n and another which is greater than n and so on. Right? So once we say it is n-dimensional, all the bases will have n element. But you can have an infinite number of these bases here, right? Yes. So as an example, Rn is finite dimensional, right? So Rn is finite dimensional, with E1 equal to 1, 0, 0 0, E2 is equal to 0, 1, 0, 0, 0, and so on. And similarly, up to En will be equal to 0, 0, up to 1. So this is, as I said, this is the canonical basis or the natural basis for Rn. But this is just one basis. There can be an infinite number of other bases as well. Fine. Then, and then already given you the other example that LP is infinite dimensional. LP is 0, 1, infinite dimensional. Finite dimensional. Oh, fine. So these are just some examples of this. Okay. And then the components are unique. So that is also another point. Let me just mention that. So the components with respect to a given basis are unique. So components of U with respect to a given basis are unique. So try to show that it's not very difficult. Typically, the way this uniqueness proofs work is that you assume that it is non-unique. Okay, so try. So say you have some U1, U2, U3, and maybe let's say U1 star, U2 star, U3 star is another set of components. Then you try to show that U1 is equal to U1 star, U2 is equal to U2 star, and so on. So it's fairly simple. You just have to use the linear independence of the basis vectors in order to show that the components with respect to a given basis are unique. Okay. So that proof I will leave it to you. Fine. Now, again, let's move on to the next result. So let V be an n-dimensional vector space, an n-dimensional vector space, and then subset F1, F2 up to Fm of V, where 1 is m greater than n, cannot be a basis, right? Cannot, because we have already shown, right, that basically it will be linearly dependent, because in the previous theorem we have seen that n is for an n-dimensional vector space, n is going to be the number of elements, right? So so this again, this cannot be a basis from the previous theorem, right? From previous theorem. Okay. Then the next thing is m less than n. That is also not possible, right? M less than n. I mean, that cannot be a basis. That's what they are saying. Cannot be a basis, right? Because it has to have an element. So has to have an element. Has to have an any basis has to have an element. So it's an n-dimensional vector space, so it cannot be a basis, right? Okay. So so basically, this case I have already given you that example, right? That E1 was 1, 0, 0 and E2 was 0, 1, 0. So here your m is less than n. It's a three-dimensional vector space, so n is equal to 3 and m is equal to 2 because I am just considering these two vectors. So then we know that this cannot be a basis because 0, 0, 1 cannot be expressed in terms of this. So we know that already. Yeah. So okay. So now the next theorem is a very, very useful result, and we can basically we can it gives a nice method for figuring out whether so suppose if you are given one basis, it gives you a nice method to figure out whether another set is a basis or not. Okay, so this is a very, very nice theorem which tells you how to do that. Okay, so let us see that now. Yes, so yes, let us see this. So this is a theorem now. Theorem let F1, F2 up to Fn be a subset. Be a subset of an n-dimensional space, an n-dimensional vector space V, right? Okay. Then let E1, E2, and so on to En be one basis for this. Be a basis. Be a basis for V. Okay. So now, see, okay, so I do not know, I want to find out whether this F1 up to Fn is a basis or not. Okay, so it has n elements because we saw that it cannot be less than n and it cannot be more than n, so there are n elements. Now we want to test whether this is a basis or not. And one basis is given to us, this E1, E2, En is given to us, and we want to find out whether this is a basis. So this theorem tells us how to find out whether this F1, F2 set is a basis or not. Okay, so in this particular case, since Fi is a subset, you can express every element of this particular set in terms of the basis vectors because these are all elements of V, right? So each Fi can be expressed as Fi is equal to beta ij Ej. Okay, so that's how we can express this with ij running from 1 to n. I equal to 1 to n, and j also runs from 1 to n. So now let's come to the statement of the theorem. So I will write TFAE. So TFAE stands for the following are equivalent. Okay, so these are some of the abbreviations that I will use. So one is that F1, F2 up to Fn is a basis. Two is that F1, F2, and so on up to Fn is linearly independent. And 3 is that determinant. Of beta ij is not equal to 0. So these are the three. Okay, what do we mean by equivalent? Okay, equivalent means that 1 implies 2, 2 implies 1, 2 implies 3, 3 implies 2, 1 implies 3, 3 implies 1. So that is what we mean by equivalent. Okay, so that's so let us try to show that 1 implies 2 implies 3 implies 1. So that is the way we will prove this particular theorem. So that is what we mean by equivalent. So that means all of them are necessary and sufficient conditions for each other. That's what we mean by equivalent. Okay, so we'll show, so prove now. So prove will show that 1 implies 2 implies 3 implies 1. Okay, so that's the way we'll show it. Now, okay, see, there are no standard rules. Whenever, suppose if you have a set of statements like this, 1 implies 2, 1, 2, 3, and if I say following are equivalent, there is no standard way that, I mean, it need not be always the way that I have said. One could, for example, try and show that 1 implies 2, if I could also show it in this particular way, and I could also show this. So this is also allowed. Okay, if I have a set of 3 statements and I want to show that all of them are equivalent, then this is also allowed, but this is also allowed. Okay, so here you can see that this completes the circle, right? So if so actually 1 implies 2 implies 3, that implies 1, and so that implies 2 again, right? So that means 2 implies 1. So actually, I mean, these statements are the same as trying to show this, so that you can convince yourself about that. Fine. Now, so let us try to show first that 1 implies 2. So this proof is trivial because, see, we have assumed that 1 is a basis. So automatically it will be linearly independent just by the definition. So 1 implies 2 is trivial. Correct? So this is just by definition. Right? Just by definition of a basis. Definition of a basis, they will be linearly independent. Okay. So you'll often see in all the theorems that we will do that one implication will be trivial, but the other implications will be quite difficult. And so this will be a pattern that you will see throughout this particular course here. So now let us try to show 2 implies 3 and 3 implies 1. So both these proofs will be quite non-trivial. Okay, so let us see that. So 2 implies 3 will be quite non-trivial. Okay, so 2 was the statement that f1, f2 up to fn is linearly independent, and 3 was the statement that determinant of beta ij is not equal to 0. Okay, so now suppose, so this is again one point of logic that you should appreciate. Suppose if I want to show that A implies B, okay, then that is completely equivalent to trying to show that not B implies not A. Okay, so this is a point of logic that you have to appreciate. This statement is not equivalent to not A implies not B. So you have to be very careful in the way you. So for example, these kind of statements you can sort of understand very easily by drawing a Venn diagram like this. So you just draw A and then you draw B, right? Suppose so A implies B means this kind of a Venn diagram, right? That whatever is within A that lies within B. So that is what I am claiming is that is completely equivalent to not B implies not A. So not B is this region, right? Whatever is outside of B is the not B, and not A is larger, right? Because that's this. So not B will be contained within not A. So A implies B is the same as trying to show that not B is in. So sometimes it is easier to prove not B implies not A, like in this particular case here. So here, what I will show is that not B, not means a negation, okay, not, I'm just using a short form, implies not 2. So, what is not 3? Determinant of beta ij equal to 0, right? That is not 3. So, here let us start. So, that means, determinant of beta ij is equal to 0, and I want to show that f1, f2 is linearly dependent, right? That's what we want to show here. Fine. So since determinant of beta ij is equal to 0, there exists alpha I equal to 1, 2, up to n, not all 0, such that beta ij alpha I is equal to 0. Correct? So that is because it's a singular matrix, right? And the moment you have a singular matrix multiplying a vector and if the right hand side is 0, that means a non-trivial solution exists, right? So that is this non-trivial solution that we are writing here. There exists alpha I, not all 0, such that this particular statement holds, right? So thus there exists alpha I, not all 0, such that alpha I fi is equal to alpha I beta ij ej is equal to 0. Correct. So that I'm just forming this linear combination here, alpha I fi, and each fi can be expressed in terms of the ej's. So that was within the statement of the theorem itself, that each fi can be expressed as beta ij ej, and so I can write this combination. This is equal to 0. Now the sum of the alphas are not 0. Correct? So that means now by the linear so what that says now. So let me just write it down here. So actually this statement here that this 0, right, this is equal to 0 actually follows from this one. Okay, so what we have now shown is that there exists some alpha i's such that this alpha I fi is equal to 0. So that means your fi's have to be linearly dependent, right? Because there exists some alpha i's which are non-zero such that this holds, right? So this implies now that your fi's are linearly dependent. Linearly dependent. And that is exactly not of 2. That is exactly not. Because 2 was a statement that the set fi 1 to n is linearly independent. So the negation of that is that it is linearly dependent, right? So that is exactly what we wanted to show. Fine. Now the last part of this particular proof. So let's go to that. So we want to show that 3 implies 1. Okay? So 3 implies 1 is the statement now that determinant of beta ij is not equal to 0, and we want to show that fi is a basis. Okay, so let us try to show that. So now 3 implies 1. 3 implies 1. Oh, that's what I'm going to show now. So, okay. So now alpha I, fi, I can write as beta ij alpha I times ej is equal to 0. Suppose if I start with this particular statement, then now this implies, so since E1 up to En is a basis, right? Is a basis, hence it is linearly independent. So that means this has to be equal to 0. Right? So that means this implies now that beta ij alpha I has to be equal to 0. Correct? And now we are given that beta ij is a non-singular matrix. So that means your alpha I has to be equal to 0. Right? Because since determinant of beta ij is not equal to 0. So basically, see, it is like a matrix multiplying a vector equal to 0, and this is a non-singular matrix. So just multiplied by the inverse, right? So suppose beta matrix, just multiplied by the inverse of that matrix, you will get that alpha is equal to 0. So now, when we started out with this statement, it is implying that alpha is equal to 0. That means your fi has to be linearly independent, correct? So this implies now that fi is linearly independent, right? Linearly independent. But that itself is not enough, right? See, for a basis, just one statement is not enough. Just the fact that they are linearly independent is not enough. We also have to show that every element of V can be expressed in terms of the fi's. So that is still remaining. So let us try to show that now. Okay, so now, so let now gamma ij denote the inverse of beta ij. So this square bracket is just indicating the matrix. Okay, so this is like beta 1 1, beta 1 2. So this is the matrix that is formed from the betas. Gamma ij is exactly the inverse of that, right? And the inverse exists because determinant is non-zero, right? So that is why the inverse exists. So basically you have now gamma I j beta jk is equal to delta ik, right? In our integral notation, this is just the identity matrix. So we have this particular relation here. Then now gamma I, so let me just write gamma I fi, that is equal to gamma I, gamma ij fi, gamma ij fj is equal to gamma ij. Then this I will write as beta jk times ei. So this is ek. So this is equal to, now they are inverses of each other. So I can write this as delta ik, ek, and that is equal to ei. Okay? So just like I can express f in terms of e. Now I can express the E also in terms of f. in terms of the inverse coefficients here. So now we are given that u is equal to ui ei, right? We can express any vector in terms of the basis vectors. Now each e can be expressed in terms of the gamma ij fj. So this will become equal to gamma ij ui fj. So basically now what we have shown is that every element can be expressed in terms of the fj's. So and hence fj is a basis, because we have first we showed that it is linearly independent. Now we have shown that every element of V can be expressed in terms of the f vectors, and hence it qualifies as a basis. Okay? So thus now what we have shown is that f1, f2, fn is a basis. Okay, so as I said, this is a very powerful theorem. So suppose you may say, what is the importance of this theorem? So I'll just tell you. So suppose I ask you, just randomly, suppose if I make up some 0, minus 1, minus 1, and minus 1, 1, 1. Is this a basis for R3? So I randomly make up some like this. Now, suddenly if I ask you this, okay, in the three-dimensional case, you may be able to do some guesswork and then maybe you may be able to figure out. But imagine now I have a 100-dimensional vector space, and now I have 100 such vectors, huge. This will just go on. And I will give 100 such vectors with 100 entries. Now I ask you, figure out if this is a basis. It will be almost impossible without this particular theorem. So what we do is that you can now express this basis in terms of the canonical basis, right? 0, 0, 0, 1, 0, 0, 0, 1. So express the 0, 0, 1. So express these things in terms of this matrix, which is connecting it to the canonical basis. Figure out if the determinant of that matrix is non-zero. If the determinant is 0, it is not a basis. If the determinant is non-zero, it is a basis. That's it. So it's a very powerful theorem to figure out if a given set is a basis for a finite dimensional vector space or not. Okay, I think we will stop here for today. Yeah, I think we'll stop here.